number of carbon atoms that goes into a reaction is always equal to the number of carbon atoms that emerge, and that is because the nucleus is not affected. A carbon nucleus specifies that this is going to be a carbon atom because it has the right charge. Set it out somewhere and it will acquire electrons until it is neutral. So a nucleus identifies the chemical structure of the element. And because the nucleus does not participate in these electronic rearrangement issues, elements are immutable, and the project of alchemy of converting the element gold into the element lead or the other way around is completely hopeless. Now, this is a brilliant and successful picture of the world, and Newton's universe is becoming richer and at the same time better understood. And there are those who speculate at the end of the 19th century that physics is all but resolved, but there are a few niggling problems. One of them that we can understand is this issue of atoms. So imagine the simplest of all atoms, a hydrogen atom. It has a nucleus with charge 1 and 1 electron orbiting it. This electron is in motion and in fact is accelerating. It's moving in a circle. And an accelerating charge will create changing electric and magnetic fields. This means it will create radiation. The radiation will carry off energy. The electron will lose energy. And as we know, you have some particular amount of energy determines your orbit. As you lose energy, you fall to lower and lower orbits. So what you expect the electron to do is to spiral in towards the nucleus while continuously emitting radiation. Atoms obviously are observed to be stable, and the stability of the atom is a big riddle. Similarly, why is it that atoms only emit at discrete frequencies? You can easily imagine that an electron revolving around an atom would radiate at the frequency. The periodic nature of the radiation would be related to the periodic nature of the motion. But Keplerian orbits, as we know, exist at any radius, and given a radius, you can figure out the frequency from p squared equals ka cubed. And so, since you can orbit at any radius, you can orbit at any frequency, and therefore you would expect atoms to be able to emit radiation at all wavelengths. What is this discrete line spectrum? And then there are some experimental puzzles. These are sort of theoretical thought puzzles. There are experimental situations in which light is observed to have particle-like behavior. Remember, Newton said light was a particle, and it was one of the rare times he was wrong, but not quite. And so this is first conjectured by Planck in 1900 to explain some details of the shape of a black body spectrum, and then by Einstein in 1905 to explain something called the photoelectric effect. And the picture that emerges is that a beam of light can be thought of, under some circumstances, as a stream of particles. And if the light wave has frequency f, then each of those particles carries an energy which is proportional to the frequency f, and the constant of proportionality, this object h, is known as Planck's constant, and it has units, of course, of energy per frequency, or energy times time, and it is a very small amount of energy times time. So h is a very small number. It means that a beam with a non-trivial flux of energy contains huge numbers of these photons, as these light particles are called. And because there are so many of them, the fact that at any given moment a particle is or isn't impinging on a detector doesn't happen. But if you have a beam of very low power, then this quantization, as Einstein calls it, the fact that the energy of a beam is carried in discrete packets, might become apparent. And to complicate things, so we have this object that has been observed to be a wave, because Young showed that light undergoes interference, exhibiting some particle properties. And then in 1927, Davison and Germer in the US do an experiment in which they basically observe that electrons exhibit interference. Electrons, manifestly particles, exhibit some of the properties that we said were the hallmark of wave behavior. So there's this weird duality emerging between waves and particles. What is a particle sometimes behaves like a wave sometimes behaves like a collection of particles. And all of this is resolved over the course of the teens and 20s of the 20th century by a beautiful and to this day somewhat puzzling theory called quantum mechanics. which leads to a complete revolution in our understanding of nature. This is the first time that we go way beyond anything Newton could have imagined, let alone written down. And this is modern physics, as we call it, 20th century physics. And in quantum mechanics, particles, all the states of a particle, rather than being described by their positions and velocities, are described by something called a wave function. And this wave function has the property that its value at any position in space at any given time predicts the probability of finding the particle, the probability density technically, of finding the particle at that point in space at that particular time. And notice I said probability and I said state, so the full state of the universe only predicts the probabilities for particles to be here, there, or anywhere else. There are not definitive predictions. It's not that our ignorance prevents us from knowing it. In quantum mechanics, the universe does not know where a particle is, and yet the deterministic evolution that was so satisfactory about Newtonian mechanics is in some deep sense retained here, in the sense that the evolution of the wave function itself is completely deterministic. The results of measurements, however, can only be predicted with probability. Again, when the numbers of particles are on the order of a mole, then the law of large numbers guarantees that these distributions will be very sharply peaked, and the probability that I am not here right now but somewhere else is exceedingly low, and I don't need to worry about it. Now, associated to this, a particle is associated a wave. This wave has a wavelength. The wavelength is determined by the particle's momentum, and again that Planck's constant thing shows up. The wavelength is related to the momentum by this relation lambda is h over p. So again, h is a very microscopic number. Macroscopic values of momenta lead to negligible wavelengths, and therefore the wave behavior of a macroscopic object is completely negligible, and you won't see it. Only at microscopic distance scales can you observe real quantum behavior. Now, we won't have time to discuss either the nature of this beautiful theory, sadly, or all of its consequences, but a few that are important to us. First, I said this resolves the issue of the discrete spectrum. Indeed, solving the equation for this wave function for electrons in an atom, you find that electrons can only occupy a discrete set of energy levels. The energy of an electron can be, in an atom, can be one of a few discrete values, and in a hydrogen atom, for example, this is the form that these energy levels take. K is some constant, and the energies are, of course, negative. These are all bound states, and the energy levels are some constant divided by n squared, where n can be 1, 2, etc. So 1 is the lowest energy, and as n gets bigger, you get states with larger and larger energies tending to 0 as n becomes large. And the point is that the dominant interaction between an atom and radiation is the emission or absorption of a single photon. One atom emits one photon, one light particle, and at the same time, the electron undergoes what we call a quantum transition between energy levels. And then energy conservation guarantees that, for example, if a photon is emitted while jumping from level n to level m, in which case the energy n must be bigger than m, then energy conservation says the energy taken away by the photon, which is hf, is the difference between the initial and final energy. The energy lost by the atom is equal to the energy taken away by the photon, and plugging in our value, we get this answer. And indeed, these frequencies, you can convert them to wavelengths, are observed in the spectrum of the hydrogen atom, for example. And so the discrete energy levels are very nicely explained by this, and many other phenomena are explained. As one outcome of this that is very crucially important to us is the Pauli exclusion principle. Pauli exclusion principle states that electrons are a kind of particle later termed fermions, and it tells us that at most 2 electrons can occupy a given energy level or a given state. And for those who like to think about these things, electrons have spin. They can have 2 different spin states. 1 electron can actually occupy a given state, but that state information includes which of the 2 spin states. it's in. The fact that electrons cannot be compressed and you cannot have more than one electron in a given state explains many things. It explains the structure of the periodic table and all the regularities that Mendeleev had found in the chemistry of elements in similar positions in the periodic table are explained by understanding the structure of energy levels and pairing it with this Pauli exclusion principle. It also explains why when I slam the table with my hand doesn't go through the table. Remember that my hand is mostly empty space. Each atom of my hand is mostly empty space, so it's not that there's really literally a collision between atoms. What's really going on is that both in my hand and in the table, all the low-lying energy levels are filled. In order to take a mole of electrons from my hand and mix them into a mole of electrons that are the local part of the table, you need to excite a mole of electrons to slightly higher energy levels that are not yet occupied. Per electron, that's not a lot of energy, but a mole is 10 to the 23 electrons is a lot of electrons. It takes a lot of energy to excite so many electrons to the next energy level. And if I hit the table hard enough to generate enough energy to excite a mole of electrons to the requisite energy level, then I've exerted so much energy that either the chemical bonds in my hand or in the table will break, and one of the two objects will just fall apart rather than moving right through each other. So this Pauli exclusion principle explains much of our day-to-day experience. It'll also become very important in understanding some phenomena in astrophysics. Phew! That was a busy week. We have found a ton of new science, and we've come a long way since Newton, not to mention Aristotle. There are many phenomena both on Earth and off of it that we understand, and the main tool that allows us to be so insightful is that atoms are fundamentally the same wherever you go. The behavior of a hydrogen atom on Earth right here is indistinguishable from the behavior of a hydrogen atom out in the Crab Nebula or inside the Sun. There may be physical circumstances that are different in the Sun, but if we can emulate those circumstances, hydrogen atoms are hydrogen atoms, helium atoms are helium atoms. The laws of physics are the same here, there, and everywhere, and so these laws that we've discovered by measuring things in labs on Earth can be and are applied to the way things behave in the heavens. Remember, we said that we were going to do Aristotle one better by looking for laws that are valid on heavens as they are on Earth, and indeed, these are the laws that we are going to find. There's a satisfaction in understanding all these things, and I hope that you will take away from this discussion a new way of looking at things you see here on Earth. But the purpose of this class was to talk about things away from Earth, and we're finally ready. When we come back next week, we will start to take all this amazing new arsenal of tools we've developed and apply it to actual astronomical phenomena. In the meantime, get some good rest. You've certainly earned it.